Okay, let's get going again. Everything look okay still? Just tell me if there's any problems. Alright, so we were finishing out this equation. We were solving for this t variable, so it looks like we had this term. Anything multiplied by t shows up in the denominator here, so we're going to have m steam times cw. That was the last thing I was writing when things just crashed. And then the last one has plus m ice, and then times the specific heat of water. I'm going to write over here that the specific heat of water that I want you to use is 4190. That's in joules per kg degree Celsius. So now here's what you could do. And I think this is, honestly, this is the best thing you can possibly do for like saving time on a test. You can write out the equation, and then you can just write the answer. Because every piece of information has been labeled clearly here, right? We have mass of ice, mass of copper, mass of steam, specific heat of water, this stuff. I already plugged in the 100, and I plugged in the zeros. And then specific heat of copper. Every single term that's here is written on the page, right? And if you're doing your work neatly and clearly like that on a test, you don't need to actually write all the numbers out. You can if you want to, but you don't have to. So can you all calculate what that is for me without me writing all the numbers in? And I guess I need to grab my phone so I can calculate it here. Be right back. That was fast, and I think that's the right answer. Because I was looking at my notes from last year, and I think that's what I got to. Can someone else verify they got the same thing? Coming from this term. Troy, can you see that? Look at it for a second, and if you can't see it, I'll show you. Again, just what I asked you all to do was to work out the algebra yourself, Troy. Did you try to do that? Maybe you tried to do that, and that's why you're asking. I think if you do the algebra yourself, you'll get the exact same thing. No, if you pull out a t, you'd get 1 minus 100 over t. There's no t in that term. You got to distribute, right? You got to distribute through here. So you'll get a term that's m steam cw times t. That one ends up basically here. And then the other term is going to be m steam cw times negative 100. That term has been added to the right-hand side of the equation, basically. You also, thank God, I don't want to type this in. Yeah, 86.1. Great, that's the answer. And now we go back to our assumption. We say, was our assumption correct? Well, I don't. If the final temperature is 86 degrees, that's totally consistent. I mean, it's totally reasonable. Possibly if, if we'd added a lot more steam, for example, like let's say we added like 10 times as much steam, based on this final temperature, my guess is that our assumption would have been wrong. And in fact, it would have been steam plus water, right? Thank you all for checking that out. I'm glad you all got the same answer. But you all understand what I'm saying? Like, first of all, if our final temperature here was like 120 degrees Celsius, we would have known that our assumption was wrong, right? Because you can't have liquid water at 120 degrees Celsius at 1 atmosphere pressure. So, anyway, that's just a nice little review problem, and it also contains something that we didn't see before, which is good, which is the fact that you have to deal with the phase changes when they go from hot to cold as a negative phase change, and just wanted to make sure we covered all our bases. So, any questions? So, if we just remove the ice from the situation, Probably. That seems like probably what would happen. I don't know though. The real question is, you know, seems reasonable though. You could check by just deleting this term and this term, right? And seeing what you get for your final answer. So when I think the only reason they mention the pressure here is because the state of the gas, liquid, or solid of a substance depends not only on temperature but also on pressure. So if the pressure of the steam had been higher, then we wouldn't really know what to do in this kind of problem. We'd have to kind of rely on some stuff we haven't learned yet, right? So I don't think we have to worry about the pressure. I think they tell us it's 1 atmosphere just to let us know. Just to be clear that, yeah. So I'd say don't worry about it. All right, so we got a little sidetrack there. It's 10:30, and we're going to take our break in 15 minutes, which means I think it's safe to go ahead and start talking about the next subject, which is conduction. So let's do that. So just to go back to what Troy said before class, that's kind of the end of what you're expected to know for the exam. And now we're just going to kind of go into new material, because we have to. We kind of got to keep going. I can't just waste a whole day, especially when we only have 2 hours per week of lecture. I'm really feeling it. It's hard to keep up, but I'm doing my best. Alrighty, so heat transfer. The first one we're going to talk about is conduction, which is these 3 things right here. All right. Actually, let's make these a little smaller. There's a lot of information here. So let's talk about what conduction is. So this is a heat transfer that occurs due to things that are touching each other. So for example, if you pick up a cup of coffee, right, and you notice that it's hot, right, your hand feels hot, that's conduction. Because the molecules of the coffee are touching the molecules of the cup, which are touching the molecules of your hand, and they can directly transfer heat because of that, right? Conduction is probably the type of heat transfer that you're the most familiar with. There are going to be 3 types of heat transfer. It's conduction, convection, and radiation that we're going to talk about today. So conduction refers to anytime you have something that's touching something, right? Just to give you some idea of like just why this occurs. So if you take if you have like a fire, right? So if I have like a bunch of pieces of wood and I light it on fire, so we have some fire right here, okay? And if I were to take, like, let's say a metal poker, let's get color for metal, maybe this right here, and I stick it in the fire, right? So I take a piece of metal, maybe it's, I don't know, iron or something like that, right? And then I'm standing here, and I hold the end of the rod in the fire, right? What's going to happen to this piece of iron as I put one end in the fire? What's going to happen to it? Is it going to heat up? Is it going to cool down? Is it going to melt? It's going to heat up. Which end is going to get hot first? The part that's touching my hand or the part that's touching the fire? It's kind of a stupid question, right? This part's going to get hotter first, right? Okay. So, what's that going to look like? What happens to a piece of iron when you put it in fire and you hold it there for a long period of time? Does anyone know? Yeah, it starts to glow. Exactly. It starts to glow. So this end down here is going to start to glow red hot, right? It's going to get red, indicating that it's very hot and you definitely don't want to touch it. What about where your hand is? Is your hand going to get hot? Are you going to be able to feel the... Yeah, eventually. Now, not immediately, okay? Not immediately. But if you leave the piece of iron there long enough, and if it's small enough amount of iron, then eventually your hand will also get hot, because if one end of the metal heats up, the rest of it can heat up as well. Now, of course, this is going to depend on what's going on around this area, though, right? Because while the heat can flow in this direction, heat can flow up the rod. At the same time, the rod is going to be being cooled by the surroundings, right? So the air around the rod is going to be cooler than the temperature coming from the fire, right? So whether your hand actually gets hot or not is going to depend on basically the rate of heat flow, right? Which is better? Is the heat going up the rod faster than the rate at which the rod is cooling due to the environment, right? And that's what conduction allows us to figure out, and that's what this equation that's here that we're going to look more into is going to tell us. So different metals, right, have different conductivities, right? Different substances have different conductivities. So if I was to try the same kind of experiment, but instead of putting a piece of metal, instead I take a long stick. Oh, I thought it was on a different color. Oops. If instead I take a long stick and I put it into the end of the fire, right? So here I have wood. I can pretty comfortably hold a piece of wood in fire for a long period of time and it's never actually going to get hot, right? Only one end of the wood is going to be hot, right? Just this side, the part that's touching the fire. And it'll start to burn, you know? And I guess eventually if it starts to light on fire, it could eventually creep up this way, but that's usually not what happens. Normally what happens is that the part that's touching your hand is cold or cool, and the part that's touching the fire ends up being hot, right? So with metal, heat can flow along the metal, but with wood, the heat kind of just stays right at the end, pretty much. Does that seem like what you all have experienced? You can take a piece of wood, you can stick it in fire, and your hand's not going to get hot from that, right? Because the wood has low conductivity. And we can see that in this table right here. I don't know how well you can or can't read this, but it doesn't look like iron's on here, but you can see that there's a bunch of metals, and over here are their conductivity. Conductivity is the rate at which heat can transfer through them. For the metals, the numbers are really big, for everything except for mercury. Things like copper, brass, aluminum, silver, steel, these are all very good conductors of heat. They're also good conductors of electricity, because it turns out that the thing that's actually allowing the heat to move through a metal more easily than moving through wood is what are called conduction electrons. Free electrons that are able to move around inside the metal, seemingly unaffected by the fact that they're supposed to be attached to an atom. Do you all know about this? Pieces of metal have between 1 and 2 electrons that are in the outer shells of their atoms. And those electrons are not bound to the atoms. They're very loosely bound, I should say. And as a result of them being loosely bound, the electrons can move around. And they can carry energy with them. So one of the main reasons why metal is a good conductor of heat and electricity is because the thing that does the heat conduction is the electrons, and the thing that does the electricity conduction is the electrons as well. Is that something you all learned about at any point? I remember, I don't know, a long time ago when I was in probably like 7th or 8th grade, I remember in my textbook, they were talking about electricity, and it says something like, you can think of metals as seas of electrons, because the metal is basically just full of free electrons that can flow back and forth, that can create waves, that can, etc., etc. So it's like an ocean of electrons or a sea of electrons. That's what I learned originally. And then, you know, as I went farther along and I took chemistry, like you all did, you learn about valence shells, you learn about the electron structures, and you learn that the electrons that are really far out are kind of like loosely bound, and so they can interact, and this is kind of responsible for things like how certain bonds are formed, right? Like ionic bonds or covalent bonds, etc. But it also affects heat and electricity, so it's all connected to electrons. Electrons are so incredibly important in really all science. I mean, they're the things that, like I said, they affect chemical bonds, all kinds of other things in chemistry I'm sure that I don't even know about. They also affect some of the properties of materials, in this case, conductivity. And, yeah. So down here at the bottom, if you compare these numbers here to the numbers for the metals, you can see that things like bricks, concrete, cork, glass, styrofoam, and wood, these are all basically insulating materials, and you can quantify just how well they work as insulators by the fact that all these numbers over here are very, very small. I think the smallest number on this chart appears to be, I guess, styrofoam and wood. So it seems like styrofoam might be one of the best insulators, at least that's listed here, until you come down to the bottom. And you notice that gases, like air is an even better insulator than styrofoam is. Argon even better. Oxygen's about the same as air, not too surprising. Hydrogen and helium even better insulators, right? So numbers that down here that are really low means that these substances are good insulators, which is why we make homes out of bricks, because bricks are good insulators. It's why we fill the walls of our homes with air. There's huge amounts of air in the walls of your home. You know, it's like you've got the outer wall, you've got the inner wall, and you've got studs, but other than that, the majority of the insulation in your home just comes from air, which is obviously a really cheap building material, right? Because it's free, since the air is all around us. Okay, so that's the theory. We'll look at the math here in a second, but you have any questions? The units in the table are in fact watts per meter, and I'm sure this is supposed to be in the denominator, right? It's watts per meter, and then it's the kelvins in the denominator, Matthew. Right, it's watt over meter times K. I hate this so much. Just looking at that, it bothers me so much. You just put parentheses around there. Do something. Write it as a fraction. It's not that hard. Anyway. Alright, so we got the idea of what conduction is. Heat transfer due to direct contact. This is the most common way that you experience heat. You know, you pick up a cold glass, it feels cold. You touch something that's hot, it feels hot. You walk outside on a hot day, and it feels hot on your skin, right? You jump into the ocean, and it's cold. That's conduction, right? Anytime something touches, that's conduction. Because it allows the molecules of one substance, the molecules of the other substance to jiggle next to each other until their jiggling averages out and they have pretty much the same temperature, at least at the contact point. Now, the way in which we quantify this is by using this equation right here. So this is our rate of heat flow, symbol is H. So H is, it's not heat, it's heat flow, which means it needs to be the energy per unit time, that's dq dt. And then here's all the stuff that it depends on the right side. You have K, which is the thermal conductivity, right here. You've got the area, because if you want to have good heat transfer, you want to make sure you have a lot of area touching, right? Just as an example, if I take something that's cold and I just touch my finger on it, the area of contact is just the area of my fingertip. And while my fingertip gets kind of cold, it's not getting cold very quickly because there's such a small cross-sectional area. But if I put my entire hand around this, then there's a lot more surface area, which means that there's going to be better heat transfer, which means my hand is going to get colder faster. I think that's pretty logical. The other things that matter are the temperature differences. So the heat transfer is going to be bigger when you have a big temperature difference. So if you have a temperature difference of only a degree, like if one object is 20 degrees, the other object is 19 degrees, then the numerator is just going to be 1. But if you have an object that's 100 degrees and an object that's 0 degrees, it's going to be 100 times more efficient at heat conduction. So big temperature difference is good. And then finally, how far are we actually trying to send the heat across? So this is where this picture comes in. So we have a hot object, we have a cold object, and we have something connecting the two of them. The thing connecting the two of them is going to have a cross-sectional area A and a length L. And what these pictures are designed to show you is that by doubling the cross-sectional area, the conductor doubles the amount of heat. Not too surprising. And by doubling the length of the conductor, it slows down the heat flow because it has to go through a larger distance, basically. So that's our equation. And we're going to look at some applications of this with a problem. 2 problems. I think we're going to do 2 problems. This is one of them. Question is, do we? This is really good. Probably a good spot to take a break. So what I'll do is I'll just put the problem we're going to do right here. Make sure everybody can see on the board, and we'll take a break. So it's 10:42. We'll take a break until 11 or 10:55.